This video is going to outline the steps of how to solve number 5, this problem right here, from your retake review, which is posted on Edmodo. So it says a plane has a heading of north 30 degrees east and an airspeed of 215 miles per hour. So what I'm going to do first is just draw a vector that represents the airplane and its heading and airspeed. So, here's my coordinate plane. Got my X and my Y axis. And this airplane, it says, is going north 30 degrees east. So if I think of this as north and east, a plane that's heading 30 degrees east of north is going to rotate in the east direction 30 degrees. So this vector has a size of 215 miles per hour, and it's rotated 30 degrees from due north. Now, if this angle here is 30 degrees, then this angle from standard position, remember standard position is lined up with that x-axis, is going to be 60 degrees. Each quadrant has 90 degrees, so 30 plus 60 is 90. Now the problem continues to factor in the wind. It says the wind is blowing at 30 miles per hour from north 60 degrees west. So this is vector 1. I'm going to look at this wind vector as my vector 2. So now I'm going north, rotating 60 degrees west. So here I'm starting due north, and I rotate 60 degrees west, and where that lands is going to represent my wind vector. Now notice my wind vector is substantially smaller than my plane vector. This wind vector is only 30 miles per hour, where my plane vector was 215 miles per hour. This rotation in here was 60 degrees. So from standard position, so from starting at the x-axis and rotating to where this vector is, that's 90 degrees plus 60 more degrees, which totals 150 degrees. That 150 degrees represents the angle from standard position. That's going to be important when we find our components. So the problem asks, it says, what are the direction angle from standard position and airspeed of this plane? So this is what the plane's heading is saying, but when we factor in the wind, we have to identify where the plane's actually heading. So what is the resultant? So if I draw a picture where I combine these two vectors, I'm adding these vectors together. I have my plane vector, which is at 215 miles per hour, and I'm going to add my wind vector. We called this the tip to tail method. When I add one vector to the other where the other one ends, and this represents 30 miles per hour. So my magnitude of my resultant is the size of the vector drawn from the origin to that point right there, to where the end of where the two vectors are added together. That pink vector that I just highlighted is what I'm trying to find. Now, some of you might have noticed that if you take this 30 degrees and this 60 degrees and add them together, you will get a right angle. This is actually a right triangle. So to find the magnitude, I could do Pythagorean theorem. I'm actually going to go a longer way to solve this, but just know that that is an option. I'm going to practice finding the components of the two original vectors, adding those components together to find the resultant vector. Okay, so if you are comfortable taking the shortcut and doing Pythagorean theorem and then finding this angle right in here, which we would call theta, feel free to do that. Okay. But I am going to practice in this video finding the components of vector 1, vector 2, and then using those to find the components of the resultant vector. Okay, so let's start up here. We've learned that to find the resultant, or to find the component of the vectors, we can use trig. So x will equal the magnitude, which is 215, times the cosine of our direction angle. And notice I'm going to use 60 degrees. I always use standard form when solving for the components of a vector. The y is going to be 215 times the sine of 60 degrees.